Good evening, all of you. Today we are going to solve that assignment 5 previous year one. Yeah. Myself, Harish Karnati. I am the Prime Minister Research Fellow at IIT Roorkee. Today we are going to solve that about transients, network transients. That the first question is find the time constant for the RC circuit in the figure below. The time constant equal to tau equal to R into C, where the C is this capacitance already given. It's 0.5 millifarad, and the R is the resistance seen from the capacitor terminals. It means it is almost same as the Thevenin's resistance only. We have to see from the that means we have to calculate the resistance seen from these terminals. That is 120 ohm, this 80 ohm, and 12 ohm. Yeah, this 120 ohm and 80 ohm are connected in parallel. That combination is connected in series with this 12 ohm resistors, right? So the equivalent resistance can be calculated as the R equal to 120 ohm, the parallel with 80 ohm. The total is connected in series with the 12 ohm, right? The equivalent is 120 into 80 by 120 plus 80, that is 200 plus 12, right? So 120 into 80 by 200, what's the value? Which is approx, just a minute, 120 into 80, it is 9600. 200 plus 12, 48 plus 12. Yeah, 48 plus 12, it is 60 ohm. The resistance seen from these terminals is 60 ohm, and the capacitance is 0.5 millifarad. So the time constant tau equal to the R into C, that resistance is 60 into capacitance is 0.5 milli. So it is 30 milliseconds, right? So the time constant of equal to this R into C, that is equal to 30 millisecond. This is option A. Where it is a one component is there. It's a storage device. One only capacitor was there. So the C equal to 0.5 millifarad. Okay, and we have to find out this R. The R is the resistance seen from the capacitor terminals. That equal to just we calculated here the resistance seen from the capacitor terminals. So we replace the voltage source with an equivalent resistance. So this 120 and 80 ohms are connected in parallel in series with 12 ohm. The 120 and 80 ohm connected in parallel, the equivalent resistance will be 48 ohm. 48 ohm in series with the 12 ohm resistor. So total equivalent resistance will be 60 ohm. The 60 ohm equivalent resistance and the capacitance is 0.5 millifarad. So the equal time constant time tau equal to R into C, that equal to 60 into 0.5 milli, that equal to 30 millisecond. Right? I hope this question is clear. We are moving to the next question. The switch in the figure moves instantaneously from A to B. Initially, it was connected to A terminal, that equal to, let us suppose, yeah. Initially, the switch is connected like this, the A to B. Sorry, initially connected to A position. Then it is at t equal to 0, it moves to that, yeah. This is at t equal to 0 position, this one. At t equal to 0 position, the switch moves to B position. I mean, instead of A, yeah, we can redraw the circuit. Before t equal to 0, the circuit is like this. It is A position and switch is close towards A position. After t equal to 0, the switch is moves to A to B. So the circuit seems like this, right? That is, it is B position. The switch is moves to A to B equal to 2 kilo ohm and 10 microfarad. Sorry, 10 microfarad. And here it is 5 kilo ohm, 10 microfarad. And it's 40 volts. Okay. Uh, what is the steady state voltage of steady state behavior of the capacitor? Capacitor, what's the capacitor equation? I equal to C into dV by dt. At steady state, the change in voltage is zero, right? The dV by dt, this term is becomes zero, right? This term becomes zero means the I equal to zero. I equal to zero means when the what is the condition to I equal to 0? It means the potential at this point and the potential at this point should be same. Then only the current flowing from 40 volts to this capacitor is 0. It means the capacitor voltage, the VC is, the capacitor is charged to 40 volts, right? Before, before this point, the capacitor voltage is 40 volts. It means the capacitor is charged to 40 volts. At t equal to 0, the charged capacitor here this capacitor is having a charge voltage of 40 volts. The charged capacitor is connected to the resistor. Here uh, this capacitor is initially charged to 40 volts and the switch is moved to B position at t equal to 0. This is, let us suppose, this interval at t equal to 0. Okay. Now what we want? Now we want this capacitor voltage Vc of t. Okay. We can apply KVL. What the KVL? I am just redrawing the same circuit with some constant, some notations like here my capacitance is C, here the resistance is R, here the voltage, here the capacitance current is IC. So the voltage across the capacitor is Vc and the this is VR. Okay. Apply the KVL in this particular loop. Consider the current is in this direction. Okay. What's the KVL? This is minus Vc plus VR equal to 0, right? Minus Vc means the we can keep it as a minus Vc. VR equal to, sorry, yeah, VR equal to this the current flowing through this loop that let us that equal to, let us suppose, consider I into R equal to 0, right? You can write minus Vc plus what is the value of I? We can write I equal to minus Ic. Why? Because yeah, here we consider the IC in this direction. However, we consider the current I in this direction. So these two currents are in opposite direction, right? So we can write I equal to minus IC, that equal to minus IC into R equal to 0. So minus Vc minus ICR equal to 0. We can write like this, right? Just I'm continuing this equation in the next case. Yeah, okay. What is the IC? IC equal to, we can write C dV by dt. And just I know this I know the capacitor current IC. I can calculate this VC, right? The VC equal to C into dV by dt. Yeah, C dVC by dt. So I'm just replacing this IC into this equation. So minus VC, just I'm moving this thing to this side, that equal to C dVC by dt into R. We can write like this, right? So minus VC equal to RC into dVC by dt. This is VC, okay? Yeah, we are just moving this dt to this side and this VC to this side and this RC to this side. So we are just rearranging these terms and we can land up with this equation, right? Minus 1 by RC into dt equal to 1 by VC into dVC, right? We can integrate both the sides. I'm just integrating on both the sides. So this equal to minus T by RC equal to ln of VC, right? Here's some constant C. Okay, you can apply exponential, then it will becomes minus T by RC. You can write this is also e power C. This C is constant and the exponential of e power C, this directly can be replaced with some constant like A, and this equal to VC, right? So Vc of t equal to some constant A into e power minus t by RC. I didn't take anything, I just solved that first order differential equation. So we have to find out this constant. Okay, what we know, at t equal to 0, we know the voltage across this capacitor, right? At t equal to just 0, before moving the switch towards the B position, we know the voltage across the capacitor, right? That is 40 volts. And the capacitor, what is the property of the capacitor? The capacitor doesn't allow the sudden change in voltage. So yeah, just a minute, I copy this equation. Yeah, yeah. The thing is, the capacitor doesn't allow the sudden change in voltage, right? So VC of 0 minus, I mean, just before to that 0 minus, the capacitor voltage is 40 volts. Due to the property of the capacitor doesn't allow the sudden change in voltage. So VC of 0 plus is also 40 volts. So VC of 0 equal to 40 volts. So we can put this to this equation. At t equal to 0, VC of 0 equal to 0, sorry, 40 volts, Just I am substituting the thing 40 volts equal to A into e power minus 0 by RC, right? This term will be 1. So the A equal to 40 volts. What is this 40 volts? This is equal to Vc of 0. That is initial condition. So we can write Vc of t equal to Vc of 0 into e power minus t by RC. This is our final equation across voltage across the capacitor, that is Vc of t equal to Vc of 0, that is initial voltage across the capacitor into exponential of e power minus t by RC. Okay. Now in this question, initially the Vc of 0 equal to 40 volts. Okay. That capacitance C equal to 10 microfarad here. After moving that switch to B position, what is the circuit? The circuit will looks like, I'm just drawing this thing. Okay, the circuit will be like this. So this is only the loop. Yeah. So the only loop is this one, right? So the resistance connected across the capacitor is this 2 kilo ohm, right? So the R equal to 2 kilo ohm. So one can write the capacitor voltage Vc of t equal to Vc of 0, that equal to 40 volts into exponential of e power minus t by Rc. R equal to 2 kilo ohm and capacitance C equal to 10 microfarad. Okay, that equal to 40 into e power minus t by 2 kilo ohm into 10 micro. What is the value? It's 2000 into 10 micro. 66 value of 0.02. Okay, 1 by 0.02 means 0.02 is 50, that equal to 40 into e power minus 50t. This is a Vc of t. Okay, the Vc of t equal to 40 into e power minus 50t. That is we can plot this waveform. Yeah, we can plot the capacitor voltage across the capacitor. This is at let us t equal to 0. Okay, initially the capacitor is, the circuit in the steady state, the capacitor is fully charged, that equal to 40 volt. Okay, at t equal to 0, we just switched from this point to this side. So the capacitor is discharged through 2 kilo ohm with a with a response of 40 into e power minus 50t. Okay, initially the voltage is 40 volts at t equal to 0, then it is regularly discharging this 40 into e power minus 50t. Okay, this is the voltage across the capacitor, that equal to 40 into e power minus 50t. The option is A. I hope this question is clear. I am moving to the next question. If you have any doubts, you can drop your question in the comment box so I can. Moving to the next question. The next question is this: the switch in the figure has been closed for a long time. Okay, this switch in the figure, yeah, this switch in the figure has been closed for a long period of time and it opens at t equal to 0. At t equal to 0, the switch is open. Okay, If it is closed for a long period of time, it means before t equal to 0, there is a steady state. In that steady state, the capacitor current IC equal to 0, right? It is 0 means the voltage, the potential across this, okay, first, yeah. It is 0 means the total current, whatever the current coming from this side, the whole current is flowing through this side, right? Whatever the current, let us suppose I0, the whole current is flowing through this. So what is the current? I0 equal to these two resistances are connected in series. So we can apply this KVL, this voltage V by R. The R total is the 10 kilo ohm plus 2 kilo ohm. That V equal to, what is the V voltage of V? Equal to 24 by 10 plus 2. It is a 12 kilo ohm, that equal to 2, sir, 2 milliamp. So what is the voltage across this 2 kilo ohm? The voltage of, just simply from the Ohm's law, V equal to I into R, that I naught into R equal to 2 kilo ohm, that I naught equal to 2 milli into 2 kilo ohm, which is of 4 volts. Okay. In the previous case, the current flowing through this, yeah, the current flowing this direction is 0, means whatever the potential at this point and at this point is same, then only the current flowing from this direction to this direction or this direction to this direction will be 0. So here the voltage is 4 volts, the capacitor voltage is also 4 volts, right? The steady state voltage equal to Vc of 0 equal to 4 volts. This is the case for t less than less than 0. At t equal to 0, yeah, at t equal to 0, the switch is opened. The switch is opened means, okay, the switch is opened means this is a open circuit. So the current flowing in the, it's not a loop. So the current I equal to 0. So we can erase this thing. I'm just erasing this circuit. Why? Because the current is 0 in this particular loop. It's not loop, it's a open loop, it's a network. So now the resistance and capacitance, right? Here the capacitor initial voltage is 4 volts. The capacitor is initially charged. Okay, it is having a charge. This charge can be delivered to the resistor, right? It can dissipate in this resistor. This resistance, which is of 2 kilo ohm. Okay, we already know that the capacitor voltage Vc of t equal to Vc0, the capacitor initial voltage, into e power minus t by Rc. That Rc equal to time constant, that is time constant tau equal to R into C. Here the C is the capacitance, which is here 40 microfarad. The R is 2 kilo ohm, 2 kilo ohm into 40 microfarad, which is of 2 kilo ohm into 40 microfarad, it's 10 power minus 6, which is of 0.08. So the Vc of t equal to Vc0, that is initial voltage is 4 volts, into e power minus t by 0.08. What's the 1 by 0.08? 1 by 0.08, which is of 12.5. So we can, yeah, 4 into e power minus 12.5 t. This is Vc of t. Okay. This equation is valid only for t greater than 0. Okay. For yeah, one can draw this plot as well. For t greater than 0, the voltage is 4 volts to it's exponentially decaying with this is 4 into e power minus 12.5 t. This is valid for only this region, that is t greater than 0. What about t less than 0? T less than 0, the circuit in steady state. This is t less than 0, the circuit in steady state. So the capacitor is fully charged. It is the capacitor voltage is 4 volts, right? So the equation is Vc of t equal to 4 into e power minus 12.5 t, which is 4 into e power minus 12.5 t is option B. Okay, I hope this question is clear. I'm moving to the next question. If you have any doubts, you can drop it in a chat box. Yeah. The fourth question is determine the time necessary for the capacitor voltage to decay to one third of its value at t equal to 0. The circuit is almost same as the previous. However, the values are different, but the circuit is same as the previous. What he asked is, what is the response of the capacitor voltage? The capacitor voltage is initially same as the previous. I am not representing any values. I am just drawing this plot. Okay. This is a plot, right? The capacitor voltage at t equal to 0, the switch is open. So the capacitor voltage is starts decaying like this. What he asked, determine the time necessary for the capacitor voltage to decay one third of its value at t equal to 0. Let us suppose at t equal to 0, it's having a voltage of Vc 0. He is asking about determine the time necessary for the capacitor voltage to decay to one third of its value. It means one third of its value means approx here. Okay. To reach this point, how much time it will takes? Okay. It's asking about this time period. Let us suppose this time period as t1. For that thing, what we have to do, we have to find out this initial voltage, that is Vc0, and we have to find out this response that equal to Vc of t by substituting this, by equating this Vc of t to this point, we can attain this value, right? The t1. Okay, we can solve this thing. Yes. Initially the switch is in, like same as previous, initially the switch is in close and the current flowing through this thing is 0. Why? Because it is a steady state, the capacitor is fully charged. So the voltage across this capacitor is, in the previous case we applied the KVL in this loop and we find out this current. Sorry, it's not 0. We find out this current. Now I am doing with the voltage divide rule directly, that is Vc of 0 equal to, we can apply the voltage divide rule, right? Voltage divide, what the voltage divide rule says, it is total voltage, that is 36 volts, into that resistance. What is that resistance? This is a 3 kilo ohm. 3k by total resistance, that is 3k plus 9k. I just applied that voltage divide rule. Because in the previous case I followed the conventional process. So to reduce the number of steps, I move to this voltage divide rule. That is 36 into 3 by 3k by 3 plus 9 is okay. 3 is 3, 3 9 volts, right? So the VC0 equal to 9 volts. That means the initially the capacitor is charged to 9 volts. Okay. Now the capacitor is discharging from 9 volts to the 0 volts. Okay. Now what we need to decay the one to decay to one third of its value. What is the one third of its value? It is one third of VC0 is VC0 by 3. It is 3 volts. Okay, we have to reach this point. That means the VC of T should has to reach this point, this 3 volts. What is the VC of T? VC of T equal to VC0 into e power minus T by RC, right? The, the 3 volts equal to VC0 is 9 volts and e power minus T by RC. The value of resistance is, now the circuit is, the switch is open. So now the circuit will be, looks like this resistance is connected. Am I audible? Yeah, yeah. Thank you. Yeah. Now the circuit seems to be like this. Why? Because here the switch is open circuited. That's why I didn't draw on this part. So now the circuit is seems like this. This R and C, the value of resistance R equal to, this is 3 kilo ohm, and C equal to, which is of 20 microfarad. Just I am substituting these same values here. R equal to 3 kilo ohm into 20 microfarad. Okay, that 3 equal to 9 into e power minus T by 3k into 20 mil, that is 3000 into 20 microfarad, 20 into 10 power minus 6, which is of 0.06. Okay, you can you can apply like this. 3 by, I'm just moving this 9 to this side. 3 by 9 equal to e power minus T by 0.06. You can apply natural logarithm both sides. That's it. Yeah, you can cancel this thing as well. 1 by 3. Natural logarithm of 1 by 3 equal to ln of e power minus t by 0.06. This ln and exponential will be cancelled. Ln of e power minus ln of 1 by 3. Ln of 1 by 3, which is of minus 1.0986, which is equal to minus t by 0.06. This minus and this, yeah, sorry, this minus will be cancelled, and that t equal to 1.0986 into 0.06, which is into 0.06, which is equal to 0.065916 second. We can write in terms of milliseconds. Yeah, we can write in milliseconds, which is 65.916 millisecond. This is approx 66 milliseconds. Okay, yeah, 65 point, already it was there. It is 65.91 millisecond. 65.92 is okay. We have to find out this thing as 65.92 millisecond. Option is A. Uh, because there they found out this VC of 0 into e power minus t also. We can also do this VC of 0 is 9 and e power minus t by, already we got this 0.06, that equal 9 into e power 1 by 0.06 means which is equal to 16.667. This is minus 16.667. This is VC of t. Okay, we can plot this response. Yeah, I will remove this. Yeah, what is the previous problem is, the previous problem, yeah, here it is VC of t. Here it is t equal to 0. Before the t equal to 0, and I will just redraw the circuit. Okay, the switch is in closed position. Okay, here the switch is in closed position, so the source is going to be delivered to resistors as well as the capacitor. That too, it is comes from minus infinite. From the minus infinite period of time, the switch is in closed, so the capacitor reached to steady state. It means it is fully charged. The fully charged voltage is 9 volts, right? The capacitor, that VC of 0 is, yeah, the capacitor is fully charged to 9 volts. At t equal to 0, this switch is open. Okay, at t equal to 0, the switch is open. So there is no closed path like this. So the current in this loop, in this particular loop is 0. So the current flowing through this resistor is 0, that I equal to 0. So whatever the charge in this capacitor, that will dissipate through this resistor, right? That's why we consider this capacitor C and this particular resistor, that is R. So whatever the voltage having in the capacitor, that will dissipate in this resistor, that will be, yeah, that will be displayed like this. It is exponentially decaying. This is of 9 into e power minus 16.667 t. To reach the one third voltage, it means this is 9 volts. What is the one third voltage? This is of 3 volts. This is only one third voltage. To reach the 3 volts, what is the time period required? Okay, to identify this point, this voltage have to equate this voltage. So this voltage whatever is there, that we equated with 3 volts. Yeah, this is the, by equating this thing, we calculated this time. That time is 60, yeah, what is this value? Yeah, 65.916. This time period is 65.91 millisecond. This much time period will takes to discharge the capacitor from 9 volts to 3 volts. I hope this question is clear. Moving to the next question. Yeah. A series RLC circuit has a resistance of 10 kilo ohm, an inductance of 0.1 millihenry, and the capacitance of 10 microfarad. What type of the damping is exhibited by the circuit? Here, the circuit is connected in series. Okay, R, L, and C connected in series. So let this current some I. Okay, what is the voltage? Voltage in this loop that equal to, we can write VR plus VL plus VC, right? This is VR, this is VL, and this is VC. Just I applied the KVL in this particular one. So the total voltage is V equal to, we can write like this, right? This all are connected in series. So V equal to VR plus VL plus VC. So what is the value of VR? VR equal to, from Ohm's law, we can write VR equal to I into R, right? What is the value of VL? VL equal to L into DI by dt. What about the VC? VC equal to 1 by C integral of I into dt, right? You can substitute these three into this one. You will end up with I into R plus L di by dt plus 1 by C integral of I into dt. Okay, this equation contains a differentiation and integration, so you can derive on both sides, then you can land up with only differential equations, right? It equal to integrate sorry, differentiate both sides. So dv by dt equal to, here R is constant, we can bring it outside, so R into di by dt plus L into d square, yeah, this I is I of t, d square I of t by dt square plus this integration and differentiation will be cancelled, so this is of 1 by C of t. Okay, you can common this L, yeah, you can make common this L, so what will happen, this R by L into di of t by dt plus, we are making common this L, so d square I of t by dt square plus 1 by LC to I of t to, yeah, so it is L. Okay, it looks like a second order equation, right? This is we can write, this is second order, we can write s square plus, which is of R by LS plus 1 by LC into I of t, you can write I of S into L. Okay, which is which is looks like second order equation. This is, you can compare this equation with standard second order equation. I just copying this equation so we can use it in next. Copy, sorry. What is the standard second order equation? The standard second order equation is s square plus 2 zeta omega n s plus omega n square, right? You can compare these two equations So you can land up with 2 zeta omega n equal to R by L. Yeah, this constant, the S constant. And this constant, that is 1 by LC equal to, yeah, omega n square equal to 1 by LC. Okay, what is the value of omega n then? You can write like this, 1 by square root of LC. So you can substitute this here, 2 zeta omega n equal to 1 by root LC. So we can substitute 1 by root LC equal to R by L. So the value of zeta will be zeta equal to R by L. This 2 will comes here, the 2, and it will be LC, right? That zeta equal to, sorry, that zeta equal to R by 2, this L and under root this L will be cancelled, it will be root L into root C. You can write like this, R by 2 root C by L, right? The damping ratio zeta equal to R by 2 into square root of C by L. You can substitute the values of R, L and C. What is the value of R? R he given us 10 kilo ohm, 10 kilo ohm, and L equal to zero point 0.1 milli, zero point 0.1 millihenry, and C equal to 10 microfarad. 10 microfarad. So the zeta equal to R by 2, that is 10 kilo ohm by 2 into square root of C by L. The C equal to 10 micro, 10 into 10 power minus 6 by L equal to 0 0.1 milli, which is 0 0.1 into 10 power minus 3. The value will be 10k, 10,000 by 2, which is 5,000 into, yeah, you can write like that, 5,000 to square root of 10 into 10 power minus 6 divided by 0 0.1 milli, that is 0.1 into 10 power minus 3, which is of 0.316. So multiplied with 5,000 into 5,000, which is equal to 1581.13. The value of zeta equal to 1581.13. What is the conditions for zeta? Sorry. Oh, yeah. If the zeta is within 0 and 1, the system is underdamped system, right? If the zeta is equal to 1, then the system is critically damped. If the system the zeta is greater than 1, then the system is overdamped system. Yeah, overdamped system. Now we got zeta is 1581. It is more than 1. It is, the system is overdamped system, right? The system is overdamped system. So what is the difference between underdamped and critically damped and overdamped means? This is a response. Let us suppose This is the final value. Let us suppose voltage. Consider the voltage V naught. If it is the system is under damped, the response voltage will be looks like with the oscillations it is going to be settled like this. If the system is critically damped, then the system is without oscillations, it is going to be settled like this. If the system is over damped, yeah, if the system is over damped without oscillations, it's going to be settled, but it will take more settling time. This is the difference between this. This is under damped. This is critically damped. This is over damped system. This is of time. Yeah, you can access these videos at this YouTube channel. It is a basic electrical circuit. The YouTube channel name. You can access these videos at this platform. Thank you very much. If you have any doubts, so you can drop it in a comment box, or you can unmute yourself and you can ask.